Good evening, everyone. This is the this is the 10th live discussion session of the course Geotechnical Engineering 1. Just a moment. Since no one has joined, I already started the class. I'll just take a moment, okay? Am I audible, Dheeraj? And is the PPT visible?
Yes, sir.
Okay. Okay. So, sorry for the interruption. Good evening. This is the 10th live discussion session of the course Geotechnical Engineering 1. Um, the topic for today's discussion is Newmark's chart and contact pressure. Okay, so in this topic, since Newmark's chart is a part of stress distribution chapter in soil mechanics, and already the basics of Bosnick's theory, Westergaard's theory has been covered in the have been covered in the last two sessions. So with only the Newmark's chart and contact pressure, I think I have gathered only a few questions. Okay, so in this session, I have seen that in the syllabus, there were no sessions on no chapters on shear stress and earth pressure theory. So after this Newmark's chart and contact pressures, some questions, I have also incorporated some questions from shear stress and earth pressure theory, because otherwise the session would not have been adequate for 2 hours. Okay, so I hope that will be okay with you. Okay, anyway, shear stress and earth pressure theory are very important chapters in soil mechanics, geotechnical engineering. So like the previous sessions, I will be first of all dictating the questions, and you need to write down the questions very carefully. There are numericals here also, numericals of Newmark's chart, and also some numericals from shear stress and earth pressures chapter. So solve the questions. I'll give you some time. Today I'll give you 15 minutes because there are some questions, uh, there are some more numericals. Okay. So after that, I'll start discussing the solutions. I hope you are sitting with your copy, pen, and calculator. So without a further ado, I'll just go to the PPT now. Just a moment. Yes. So the PPT is visible, right? Dheeraj Raghuvanshi. You can see the PPT.
Yes, sir.
Yes. Okay. Good. Okay. So again, very good evening. I'll start the 10th live discussion session for Geotechnical Engineering 1. The topic is Newmark's chart, contact pressures. Okay, someone is joining now. Rahul Shah. Uh, I haven't seen you, Rahul Shah. You have joined right now. So, is this the first class you're attending of this course? First live discussion session? Hello, I'm talking to Rahul Shah who has joined right now. Is this the first class you're attending?
Hello, am I audible?
Yes, is this the first class you're attending of this
No, sir.
particular?
I have joined a few lessons. Just
No, the
week.
Fridays, the
No,
Fridays
no,
classes, the Fridays classes. Is this the
no, no.
first time?
Recently, I didn't join. Recently, I didn't join. first few
Okay. First few
sessions I
classes
have
you have joined. So you know, right, that I'll be first of all dictating the questions. You need to write down the questions and then you'll get time to solve them and then I will start discussing the questions. This is the, this is how the
okay,
schedule
okay,
of this session progresses. Okay.
okay, sir.
So I'll dictate the questions right now. Please write them down. And if you know the answer, please don't tell them while I dictate or don't write the answers in the chat box. Okay.
Okay, sir.
Okay, you can mute yourself. Thanks. Okay, so I'll start dictating the questions now. The first question is the Newmark's chart is based on. The Newmark's chart is based on. First option, Bosing's theory. Second option, Westergaard's theory. Third option, equivalent load method. Last option, none of these. I repeat the question. The Newmark's chart is based on first option, Bosing's theory. Second option, Westergaard's theory. Third option, equivalent load method. And last option is none of these. Okay. Next question. Contact pressure depends upon the elastic properties of. Contact pressure depends upon the elastic properties of. First option, soil only. Second option, footing only. Footing means foundation. Okay. Third option, both of these. And last option, none of these. I repeat the question. Contact pressure depends upon the elastic properties of. First option, soil only. Second option, footing only. Third option, both of these. And last option, none of these. Okay. Next question. Yes. Comment on the type of foundation and soil from the given diagram. Comment on the type of foundation and soil from the given diagram. You can draw the diagram or you can take a screenshot. Just to let you know, here two parameters have been given, settlement and pressure. The variation of settlement and pressure You have to observe this variation, to observe the settlement and the pressure, contact pressure, and then you have to tell me what is the type of foundation and soil. Type of foundation means whether it is uh, flexible footing or a rigid footing, and the soil, I mean whether it is clayey soil or sandy soil. Okay, this is the thing I want to know only. Please let me know if you have drawn the diagram or taken screenshot of the same, whichever is comfortable. Let me know if you have finished the drawing or taking the screenshot of the diagram. Okay, have you finished drawing the diagram? Hello. Okay, anyway, I'll just repeat the question. You have to state the type of foundation and soil from the given diagram. Someone is messaging. Done. Okay. Here you have the settlement and the contact pressure given. Okay. Okay. Next question. In the construction of the Newmark's chart, if the number of annular areas selected is 10 and each annular area is divided into 10 sectors, the value of the influence factor for the chart is. Here annular areas refers to the number of rings, okay, in the Newmark's chart. So this question might be slightly deviating from the standard Newmark's chart, but anyway you have to answer as per whatever is given, whatever data is given in this question. In the construction of the Newmark's chart, the number of annular areas selected is 10 and each annular area is divided into 10 sectors. The value of the influence factor for the chart is, your options are 0.005, 0.05, 0.01 or 0.001. Someone has joined right now. This is to inform you that this is the fourth question. Okay, please write down the question from the current one. The topic is Newmark's chart and contact pressures. This topic. This is the 10th problem solving session. I repeat the question. In the construction of the Newmark chart, if the number of annular areas selected is 10 and each annular area is divided into 10 sectors, the value of the influence factor for the chart is: first option 0.005, second option 0.05, third option 0.01, last option is 0.001. Okay. Okay, next question. Yes. In the equivalent point load method, the accuracy of the result obtained depends on the size of the area unit chosen. Is this statement true or false? I hope you have idea about the equivalent point load method. Anyway, I repeat the question. In the equivalent point load method, the accuracy of the result obtained depends on the size of the area unit chosen. Is this statement true or false? Okay, next question. Originally, the number of sectors considered in Newmark's influence chart is: originally, the number of sectors considered in Newmark's influence chart is: first option 10, second option 12, third option 20, last option is 25. I repeat the question. Originally, the number of sectors considered in the Newmark's influence chart is: first option 10, second option 12, third option 20, last option 25. Okay. Next question. Yes. A similar question like the last one. Comment on the type of foundation and soil from the given diagram. You have to tell from this diagram what is the type of foundation, type of footing, and what is the type of soil. You have the settlement given over here in the diagram and the variation of the contact pressure from the edges or the corner to the middle center of the footing. Let me know if you have finished drawing the diagram. Have you completed drawing the diagram or taking the screenshot, whatever? I'll then move to the next question. Okay, anyway, I'll just assume that you have finished drawing the diagram. I'll go to the next question. Okay, this is a numerical. Please write down the data very carefully. A rectangular area 2 meter by 4 meter on the ground surface carries a uniformly distributed load 80 kilonewton per meter square. Find the intensity of vertical pressure at 5 meter below the center and corner of the loaded area. I have given few data. Given Kb, that is the Bosing's influence factor, as 0.0328 when m equals to 0.2 and n equals to 0.4. Okay, and the same Bosing's factor Kb equals to 0.0931 when m equals to 0.4 and n equals to 0.8. To find out the intensity of pressure at 5 meter depth below the center and then the corner of the loaded area. I repeat the question. A rectangular area 2 meter by 4 meter on the ground surface carries a uniformly distributed load 80 kilonewton per meter square. Find the intensity of vertical pressure at 5 meter below the center and corner of the loaded area. given the Bosing's influence factor 0.0328 when m equals to 0.2 and n equals to 0.4. I hope that you know what m and n stands for. If any doubt, you can ask me right now. And the same Bosing's influence factor Kb equals to 0.0931 when m equals to 0.4 and n equals to 0.8. Okay. I hope the question was clear. I'll go to the next question, which is an extension of the previous one. The previous question which I have given, if to solve the same question using the equivalent load method. Solve the same question using the equivalent load method. Okay, clear? Next question. Again, the previous question, this one. Rectangular area 2 meter by 4 meter carries a UDL of 80 kilonewton per meter square. Intensity of vertical pressure at a depth of 5 meter below the center and the corner. Okay. So now here, if to solve the same problem using the Newmark's influence chart, if the influence factor is 0.005, it is given, and the number of load blocks occupied by the area is 25.5 and 18.5 respectively. That means in the first scenario, that is for the center, when you are placing the center of the loaded area in the center of the on the center of the Newmark's circle influence chart, then there are 25.5 load blocks occupied by the rectangular area. Now for the corner, when I am placing the corner of the rectangular area on the center of the Newmark's influence chart, then the number of load blocks occupied by the rectangular area is 18.5. So everything is given. Just you have to put it in formula and find out the stress, vertical stress at the depth of 5 meter. Okay. So anyway, this area needs to be found out from the Newmark's chart, but since placing the area and on the Newmark's chart and doing the problem, it is not feasible right now. So the value, the number of load blocks occupied by the area have been given. Please let me know if you have finished writing the question and if you have any doubt regarding this question. The same question has been repeated thrice. The first part you have to solve using the normal Bosing's equation using m and n. Then the next one using the equivalent load method, same problem. And in the third part, you solve the same problem using the Newmark's influence chart. Then the number of load blocks occupied by the area for the stress at the center case and the stress at the corner case have been given as 25.5 and 18.5 respectively. Okay. Is it clear? Do you have any doubt? Is it clear? The questions? If you have no doubt, I'll just move forward. Okay. Fine. Next question. Again over here, you have to comment on the type of foundation and soil from the given diagram. The white portion over here represents the settlement and the arrow marked portion, shaded arrow marked portion represents the variation of the contact pressure. Okay. I hope you have finished drawing the diagram. Again, in this diagram, you can see the white portion represents the settlement of the foundation of the footing, and the shaded arrow marked portion represents the variation of contact pressure from the soil. Okay. Using this, you have to answer what is the type of footing and the type of soil. Again, either it is flexible or rigid, the footing, or the soil clay or sandy soil. Okay. Next question. Again a numerical. A rectangular area 3 by 1 meter is uniformly loaded with load intensity 100 kilonewton per meter square at the ground surface. Calculate the vertical pressure at a point 4 meter below one of its corners using the Newmark's influence chart if Na equals to 12. What is Na? Number of units under the loaded area. So generally conversion need to be done because the depth is not equals to 5, it is equals to 4, but here the value of Na has been already given. I repeat the question, a rectangular area 3 by 1 meter is uniformly loaded with load intensity 100 kilonewton per meter square at the ground surface. Calculate the vertical pressure at a point 4 meter below one of its corners using the Newmark's influence chart if Na equals to 12. Number of units under the loaded area is 12. Okay. Next question. Yes. Uniform intensity of loading at the foundation level of a building 10 meter in width and of infinite length is 100 kilonewton per meter square. Calculate the vertical pressure under the center line for which Na equals to 110 and the edge for which Na equals to 80 of the footing at a depth of 1 meter. So in this question, I think it is somewhat similar to the question I have given in the session of Boosing's theory, but here I have also mentioned the number of units under the loaded area in both the cases, once for the center line and once for the pressure under the edge. So we have to solve this using the concept of the Newmark's influence chart only over here. Okay, I'll be showing you that concept only. And the depth at which the vertical pressure need to be determined is 1 meter. Okay, I repeat the question. Uniform intensity of loading at the foundation level of a building 10 meter in width and of infinite length is 100 kilonewton per meter square. Calculate the vertical pressure under the center line for which Na equals to 110 and the edge for which Na equals to 80 of the footing at a depth of 1 meter. Okay, I hope the question was clear. Next question. A raft foundation carries a UDL, that is a uniformly distributed load, of 30 tons per meter square. Estimate the vertical pressure at a depth of 9 meter below the corner of the draft by Newmark's chart if the influence factor is 0.005 and the number of load blocks occupied by the area is 62. I repeat the question. A raft foundation carries a UDL of 30 tons per meter square. Estimate the vertical pressure at a depth of 9 meter below the corner of the raft by Newmark's chart if the influence factor is 0.005 and the number of load blocks occupied by the area is 62. Okay. Next question. Again, from this diagram, you have to comment on the type of foundation and soil. Here again, the white portion below the ground, that is this particular portion, represents the settlement, and this shaded portion with the arrow pointing upward represents the contact pressure, variation of the contact pressure. So using the settlement and the contact pressure distribution diagram, you have to tell me what is the type of footing over here, flexible or rigid, and what is the type of soil, sandy soil or clayey soil. I hope you are done with this. Next question. Yes, so up till this question, it is the Newmark start and contact pressure chapter. Now some additional questions, because otherwise the session won't be equivalent to 2 hour session. I've added some part from the shear strength and earth pressure theories, which are not there, which I think they're not there in the syllabus, so I will not get a chance of including them later. Okay. So the question is, in the Mohr-Coulomb failure theory, the critical shear stress causing failure depends upon, first option, properties of the material, second option, normal stress on the failure plane, third option, both of the above, and last option, none of these. I repeat the question. In the Mohr-Coulomb failure theory, the critical shear stress causing failure depends upon properties of the material, normal stress on the failure plane, both of the above, or none of these. Okay. Next question. The unconfined compression test is generally applicable for dense sands, saturated clays, weathered geomaterials, or none of these. I repeat the question. The unconfined compression test is generally applicable for, the options are dense sands, saturated clays, weathered geomaterials, or none of these. Okay. Next question. A cylindrical specimen of saturated clay 4 cm in diameter and 8.66 cm length is tested in an unconfined compression tester. Estimate the unconfined compressive strength and shear strength of clay if the specimen fails at an axial load of 465 Newton and the change in length of the specimen on failure is 1 centimeter. I repeat the question. A cylindrical specimen of saturated clay 4 cm in diameter and 8.66 cm length is tested in an unconfined compression tester. Estimate the unconfined compressive strength and shear strength of clay, the specimen fails at an axial load of 465 Newton and the change in length of the specimen on failure is 1 centimeter. Okay. Next question. A cylindrical soil specimen fails at an axial vertical stress of 160 kilopascal when it is laterally unconfined. The failure plane makes an angle of 50° with the horizontal. Calculate the values of cohesion and angle of internal friction of the soil. I repeat the question. A cylindrical soil specimen fails under an axial vertical stress of 160 kilopascal when it is laterally unconfined. The failure plane makes an angle of 50° with the horizontal. Calculate the values of cohesion and angle of internal friction of the soil. Okay, I hope the question was clear. Next question. This is a question from earth pressure theory. Okay, a rigid retaining wall 6 meter high is sustained from yielding. The backfill consists of cohesionless soil having phi equal to 26 degree, that is the angle of internal friction, and gamma, that is the unit weight, equal to 19 kilonewton per meter cube. Compute the total lateral thrust per meter length of the wall. I repeat the question. A rigid retaining wall 6 meter high is restrained from yielding. The backfill consists of cohesionless soil having phi equal to 26 degree and gamma, that is unit weight, equals to 19 kilonewton per meter cube. Compute the total lateral thrust per meter length of the wall. Okay. Last question. Compute the intensities of active and passive earth pressure at a depth of 8 meter in dry cohesionless sand with phi equal to 30 degree and gamma equals to 18 kilonewton per meter cube. Do you know what do you mean? What is the meaning of active and passive earth pressure? Do you have any idea about active and passive earth pressure? Okay, anyway, I'll just give you the basics while solving this question. Compute the intensities of active and passive earth pressure at a depth of 8 meter in dry cohesionless sand with phi equal to 30 degree and gamma equal to 18 kilonewton per meter cube. Okay, so these are all the questions. I'll give you 15 minutes time. Okay, I'll start at 7:10. It is 6:55 right now. 5 minutes to 7. I'll start at 7:10. Okay. Hello, hello. Am I audible? Dheeraj Raghuvanshi. Am I audible?
Yes, sir.
Okay. So have you completed the questions?
No, sir. Actually, uh,
You need some more time.
no. Actually, I have not studied this theory. I have to read the book first.
Okay, okay,
So,
fine. So I think I can start discussing the
yeah, please.
solutions. Okay, and you can just catch up. Okay, no worries. Okay, so I'll start discussing the solutions of the questions individually. Okay. So the first question was Newmark's chart is based on any answer? You know, Newmark's chart is based on. It is based on which theory? Bosing's theory, Westergaard's theory, equivalent load method. Okay. Newmark's chart is based on Bosing's theory. Okay. Bosing's theory is the basis, and from that, Newmark's chart has been derived. The main concepts, not the methodology, but the concepts. Okay. Okay. Next question was contact pressure depends upon the elastic properties of. I think you can take a guess for this answer. What can the
Sir,
answer
my
be?
guess is for soil only because footing is very rigid. So, expecting
Footing,
large.
no, that is the problem. Footing is not always rigid. Okay, footing can be flexible also, footing can be rigid also. Okay, so the contact pressure depends upon the elastic properties of both soil and the footing, because like soil can vary from cohesionless soil to cohesive soils, clay, sands. Okay, footing can also vary. Okay, you will see in the diagrams I've given you, you will see. Okay, so for this question, the answer will be contact pressure depends upon the elastic properties of soil and footing both. Okay, okay. Next question. Have you solved this? You haven't solved this, right? Okay. Anyway, so just see carefully. Okay, there are two parameters, right? Settlement and pressure. This is the settlement. In this diagram, you can see the settlement. This is the footing. Just ignore this part. The footing where the contact pressure is ending. This is the footing. The settlement is constant throughout, isn't it? It is constant. So when the settlement of the footing is constant, then the footing is rigid. The entire width of the footing is settling at once. The footing is rigid. Okay, the footing is rigid. Now come to the pressure, the contact pressure. The contact pressure, you can see it is minimum at the center of the footing and maximum at the side. This is the characteristic of soil which have low shear strength. Which have low shear strength. For example, cohesive soils like clays. Saturated clays or in general clays, they have lesser value of shear strength than sandy soil because they also have friction values in them. Sandy soil, loamy soils, pure sands or loams, they have friction values also in them. But clay, they have lesser amount of strength. Okay, hence at the center the pressure is lower than at the edges. So the soil is clay soil. So it is a rigid footing, and the soil is clay. So in this way you can find out. So your doubt is clear. As you have mentioned in the previous question, it does not depend on the footing. Okay, we'll just carry on. After all the questions, I think your doubt will be clear. Is this question clear? Is this solution clear to you? Because
Yes.
it is constant settlement, it is a rigid footing, and the pressure is minimum at the center, maximum at the edges. It is clay. Okay. Okay. Rigid footing and clay soil. Yes. Next question. In the construction of a Newmark's chart, number of annular areas selected is 10, and each annular area is divided into 10 sectors. What is the value of influence factor? Have you solved this? No, right? So the value of influence factor, you see, it depends on, it is 1 divided by number of annular areas or annular rings multiplied by number of sectors. Number of sectors. Okay. So in this case, number of rings is 10. Number of sectors in each ring is 10. How much? 0.01, isn't it? 0.01. This is a slight deviation from the actual scenario of the Newmark's chart. We'll get to that. Okay. So in this case, the influence factor, the Newmark's influence factor, is equal to 1 divided by the number of annular area or annular rings multiplied by the number of sectors. Okay. Here both the values for both are 10. So it is 1 divided by 100, that is 0.01. Okay. Okay. Next question. In the equivalent point load method, the accuracy of the result obtained depends on the size of the area unit chosen. Is it true or false? Okay, so Dheeraj, right? Since you haven't read this chapter, whatever I'm saying, you should, confirm the same and look all these, concepts up in a standard textbook. Okay. So you haven't
Yes,
solved
sir.
any question.
No, sir.
Okay, so you could have told me previously only. I would have started the discussion right away, because otherwise the 15 minutes I gave you was not, you know, fruitful to you. It was anyway. I think some other person was also there, but not there currently. Anyway, so in this question, the answer is true, because in the equivalent point load method, what happens is, if we have a particular loaded area, we divide it into some finite number of areas. Suppose I divide this into this way. Okay, the UDL converted to point load for this particular areas acting as a center, and if I want to find out the exact value of the stress at a particular depth z below the center of this loaded area, so from this particular sector, this is R1, this is R2, this is again R3, this is R4. Okay. So in this way, R by Z value, the individual R by Z value, for example, R1 by Z will give us a value of influence factor. Again, R2 by Z will give us value of another influence factor. So in this way we can find out the stress at any depth Z, the load divided by Z square. into summation of k b I belongs to 1 to n. Here I equals to 4 because there are 4 loaded units. So the accuracy of the result obtained depends on the size of the area. The more the number of area, the more the accuracy increases. Okay. So if I divide it into like this, then I'm using more number of loaded areas, more number of sectors in these loaded areas. So the accuracy will vary as per the number of sections in the area I have chosen. So the answer over here is true. Okay, because in any case, if the UDL was concentrated on this particular rectangle, then the value we are obtaining is Q. If the rectangle decreases to this size, then the value of Q will get reduced, isn't it? And then the value of R will also change. And for that, the value of the influence factor might also change. So in any case, the accuracy of the result will depend on the size of the area unit chosen. Sorry. I hope this was clear to you. Just a moment. This did not
Yes, sir.
update it. Yes, now it is updated. Okay. So next question. Originally, the number of sectors considered in the Newmark's influence chart. Do you know this? What is the number of area units considered in the Newmark's number of sectors in the Newmark's chart? Originally, the number of sectors considered for the analysis is 20. It is 20. Okay. It is 20, and I believe I have not asked you to find out the influence factor. Okay. So when it is 20, the influence factor will be, there are 10 circles. Okay. There are 10 circles. So it will be 1 divided by the number of circles and number of sectors. So what is the value of the influence factor over here? In the original Newmark's chart, what is the value of the influence factor? Just find it out and tell me. What? What is the answer?
Sir, 0.005.
0.005. This is the actual value of the influence factor in the Newmark's influence chart. Okay, 0.005, because there are 20 sectors. Okay. Good. Next question. Yes, so now tell me this particular scenario. What will be the type of foundation over here? In this case also, the settlement is consistent, right? Constant settlement throughout the width of the footing. So what is the type of footing over here? Flexible or rigid?
Rigid, sir.
Yes, rigid. So first part is done. It is a rigid footing. Now type of soil. Here you can see the contact pressure is maximum at the center. Okay, soil having more strength. Sand or clay?
Sand.
Yes. And also in sandy soils, what happens is, you know about the capillary suction, right? In sandy soils, granular soils, that creates a negative pore pressure which increases the effective stress. Are you familiar with this concept? Capillary suction?
Yes, sir. It is.
Yes, capillary action, it creates a negative pore pressure. And when the negative pore pressure is created, the effective stress increases, leading to an increase in the shear strength. Okay, that also happens often in sand. Anyway, in this case, the footing is rigid and the soil is sand. Okay, next question. Rectangular area 2 by 4. Okay, we haven't solved any question. I will solve it and you will just verify the same from any standard textbook or any material whatsoever. So the area mentioned over here was 2 by 4, isn't it? 2 meter by 4 meter. Okay. In the first scenario, you're asked to find out below the center. So using this ratio of m and n, m equals to b by z and n equals to, sorry, m equals to a by z and n equals to b by z. So a means one dimension and b means the other dimension. Okay, I'll just write ab later. So in the first case scenario, you have to find out below the center. So using m and n in this case, I can find out loading at the corner of any rectangular area. Okay. Now if I divide this rectangle into 4 other rectangles, if I find out the loading at the corner of these individual 4 rectangles, I'll be getting the loading below the center of this entire rectangle, isn't it? If I find out the loading at the corner of these 4 individual rectangles, I'll be getting the loading below the center of the full rectangle, right?
Yes, sir.
Yes. So for this particular small rectangles, this is 1 and this is 2, right? So for the first case scenario, I write as A, one dimension is 1 and the B and the dimension is equals to 2. Now the value of M in the first case for the center, you can mute yourself, is equals to A by Z. Hello, you can mute yourself. Yes, thank you. A by Z, what is the value of Z? Z is equal to 5 meter. So 1 by 5, it is 0.2, isn't it? 0.2. Now what is the value of N? N equals to B by Z. B by Z. That is 2 by 5 equals to 0.4. Now I have mentioned when M equals to 0.2 and N equals to 0.4, the value of KB is this one. The value of KB is 0.0328. Now the loading at the corner of each individual rectangle will be equals to Q into KB. That is the UDL into KB. Now if we multiply this by 4, we will get the loading at the center of the main rectangle, isn't it? Is it clear? You'll be getting the loading at the center of the main rectangle. Hello?
Yes, sir.
Yes. So please solve it and let me know what answer you're getting. 4 into Q, Q is the UDL, that is 80, and KB has been given, that is 0.0328. Solve this and tell me the answer. What is the value of sigma Z at the center, below the center, at a depth of 5 meter?
Sir, it is coming
Hey,
297.92.
do it correctly. Q is how much? Q is 80, KB is 0.0328.
Yeah. 10.496.
Yes, 10.5 approximately, right? 10.5,
Yeah.
10.5 kilonewton per meter square. Okay, this is the first part. For the second part, it is the corner of the loaded area, the corner of the main rectangle. So now what will be the value of A? What is the value of A right now? If I'm considering the main rectangle and the corner, in the first question I was considering this small rectangle and the corner is this one. So A was 1 and B was 2. Now I'm considering the main rectangle. Okay, and finding out the stress below this corner. Okay, so tell me the value of A over here. Yes, hello.
Sir,
What if if it was this small rectangle, the value of A is 1 and B is 2, the dimension of this small rectangle for the corner loading, right? Now it is the entire rectangle, so for the corner loading the value of A will be 2,
2,
right, and B will be 4.
2 and 4, yes. 2 and 4.
Yes, that is the thing. So now for this part, m equals to again A by Z, and that will give me a value of around, I think, yes, 0.4, 0.4, and n equals to B by Z, that is approximately, not approximately, equal to 0.8, yes, 0.8. So now the corner loading, here the entire thing has been taken at once. Okay, and for 0.4 m and 0.8 n, the value of kb is 0.0931. Now for this is the center, let's see t over here. Now sigma z at the corner. Okay, it will be how much? We need to multiply 4 right now, right, because we are considering the entire rectangle. It will be simply q into, this is kb for the center, kb1, and I right now I write kb2. I'll write over here kb1 and kb2. Solve it and tell me the answer. Q into kb2, q is 80. What is the answer?
So 7.448.
Yeah, 7.45 approximately, right? 7.45 kilonewton per meter square. Okay, so this is how you solve this sum. This is one method. Okay, now in the next question I've asked you to solve this sum using the equivalent load method. Using the equivalent load method, you can see the solution over here. Okay, for point under the center is this part A. The radial distance from the center of each small rectangle is this one, the radial distance. Okay, now I'm not using a and m and n ratio, I'm just using the radial distance from each of this rectangle, small rectangle. This is 1.117. Now r by z value is 0.223, for which from the table the kb value is 0.4247. Now qz, sorry, sigma z equals to q by z square summation of kb. So q by z square summation of kb means the same value, isn't it? Because from the center of each rectangle to the center of the main rectangle, the distance is same. Hence r by z is same. Hence the value of kb is same for the 4 cases. Okay, so it will be q by z square into 4 into kb. You get a value of 10.87. Okay, 10.87, and the last one we have got a value of approximately 10.5, right? 10.5 using the exact uh, way, the exact method. Okay, now in the second part, here also the error percentage have been calculated. You can solve it. In the second part, for the point under the corner B, this corner B, okay, this is the corner B. The radial distance from each individual rectangle to this corner B has been calculated. So for area unit 1, 2, 3 and 4, for area unit 1, the value of R is the same as the previous question. It is previous part is 1.117. Now for the 2, R2, here 1 plus 1 plus 1, this is the base, and this is the perpendicular. You can find out the hypotenuse. Okay, in a similar way, using geometry and trigonometry, you can find out the radial distance from this third rectangle center to this point B, and in the same way you can find out the value of radial distance from the center of the fourth rectangle to this point B. Okay, now after finding out the individual value of the radial distance from all the 4 rectangles to the corner B, you find out r by z, and for the individual r by z value, you find out the value of kb, influence factor. Okay, value of influence factor. Now this influence factor, you find out the summation of this influence factor. Now put in the formula, sigma z equals to q by z square into summation of kb. You get a value of approximately 7.57. In the previous method we have got 7.45, right? So this is the percentage of error. Is it clear to you? Any doubt regarding this question? You can tell me right now.
Sir, please proceed. But yeah, it is clear. But I have to learn at. I have to
Yes,
read the book.
yes,
Yeah.
I have mentioned in the first question, right? I think you remember the question. This one remember? The radial distance from each individual rectangle will give individual value of the influence factor. That has to be summated and multiplied with q by z square to get the value of space. Isn't it the same thing over here, right? The same thing, right? Could you follow the theory and the I mentioned over in the true false statement and the practical example over here? But you haven't read this chapter in theory, right?
Yes, sir. Once I will read myself, then
Yes, yes,
things will.
okay.
Yeah,
Just
yeah.
just note down the solution or take a screenshot of this, and when you read, when you go through this, you please correlate, okay? Anyway, this was the solution, and the third part was the previous problem you need to solve using Newmark's influence chart. So what happens is, in Newmark's influence chart, you have to scale the loading area, because in original in original problem the z equals to 5 meter is considered in original Newmark's chart. Okay, but all the time the z is not equal to 5, right? So whatever the loading area we get in original, we have to scale the area as per that ratio. Suppose we have to find out, for this loaded area, to find out the loading at a depth of 9 meter. Okay, so 9 to 5, we have to just do the scaling. Just a moment, I'll just check one thing. Okay, so not 5 meter, there was slight mistake, that was I was telling you. It was originally it is 5 centimeter. Okay, you will find the Newmark chart, the scale is 5 centimeter. So now if we have to find for a depth z equals to suppose 5 meter, so the scale will be 5 centimeter to 5 meter. We have to scale this entire area, into a transformed area, and now we have to place this on the Newmark's influence chart and count the number of loaded areas. Okay, since that is not feasible right now and not feasible during examinations also, what is more feasible is simply stating the number of load blocks occupied by the area. So what happens is, when we get a loaded section, we place it on the Newmark's influence chart and we count the number of blocks, sectors, number of load sectors, how many load sectors are occupied by the block. Okay, and then very simple, we do it like this. So see, for the center load, okay, now I'll just divide it into center and corner. For the center, sigma z is equals to q into if into na. Okay, now q is 80, right? Q is 80. What is the value of influence factor for the original Newmark's chart I have mentioned? You have found it out, right?
20.
No, influence factor. 20 is the number of sectors, you are correct. But what is the influence factor? 1 by 20 into 10, you have found out?
0.005.
Yes, 0.005. So it will be 80 into 0.005 into NA. For the center it is 25.5 number of sectors, right? You get a value of approximately 10.2. Okay, now for the corner, again same formula, sigma z equals to q into if into na. Here again q is 80, if is 0.005, and the value of the number of load blocks occupied by the area for this case is 18.5. So you get a value of approximately 7.4 kilonewton per meter square. Okay, so you solve this first using the actual method, exact method. You get 10.5, 7.45. Then using the equivalent point load method, you get 10.87, and 7.57. Now using the Newmark's chart, you get 10.2 and 7.4. Okay. So I hope this was clear to you to some extent. Once you read the theory, it will become much more vivid. Okay. But this is the formula which I'll be using in the next sums also. Anyway, this question. Now tell me, in this question, the settlement is not constant. So is this footing flexible or rigid?
Sir, flexible.
Very good. This is flexible. Flexible. Now see, the contact pressure is uniform. Okay, but as you can see, the settlement is maximum at the center. If settlement is maximum at the center, that means the resistance from the soil is minimum at the center, isn't it? If
Yes, sir.
settlement is maximum center, okay, so now resistance of the soil is minimum at the center. Which type of soil it will be? Clay or sand? The soil is giving least resistance, least pressure at the center, so it will be clay or sand. Remember this slide, contact pressure least in the center. What was it? Now say, what is the answer? Clay or sand? Just tell me any answer, whatever you think. Hello.
Sir, clay, but not sure.
Yes, clay. You're right. Clay. Why clay? Because wherever the settlement is more, there it has got least resistance from the soil. At the center, there is least resistance. Okay. So if the reaction force from the soil would have been drawn, that would have been similar to this one, right? Least resistance, more settlement. So it is clay, isn't it? So I think it is clear, the concept is clear. How are we, concluding whether it is clay or sand? Clear, right?
Yes, sir.
Okay. So the next question, rectangular area. So we haven't solved this question anyway. These questions are very easy. I'll just solve because I did not get any variety of questions. So it is just again the same formula, Q into influence factor into NA. Okay. Value of Q is 100 into the value of influence factor is 0.005. And how do we solve this? By placing the transformed area over the Newmark chart, and then we get the number of loaded units, load blocks, that is over here given as 12. If you solve this, you'll get as 6 kilo, sorry, 6 kilonewton per meter square. Okay, 6 kilonewton per meter square. Again, the next sum, I believe the same thing, center line and at the edge. For the center line, sigma z equals to, okay, I'll just do one thing, not like this. Sorry. I'll just write the formula. Sigma z equals to how much? Q into influence factor into number of load blocks. So for the center, sigma z equals to, what is the value of Q? Q is 100 into 0.005 into 80. That will be equals to how much? Oh, not 80, sorry. For the center it is 110, right? 110. It will be 55 kilonewton per meter square. Now for the corner, 100 into 0.005 into 80, that will be equals to 40 kilonewton per meter square. Okay, same formula, just changing the number of load units. Next question also, again in a similar way, raft foundation carries a UDL. So below the corner of the raft, here also sigma z at the corner will be equals to Q into influence factor into Na. Here the influence factor is already given, it is easier. Again 30 tons into 0.005 into 62, that will be almost equal to, I think, 9.3. Please check this. Please check this calculation. Are you there, Dheeraj? Please check this calculation.
Yes, sir. Please give me some time.
Yes, yes. Okay.
Sir, it is 30 into 0.008. It is, I think, you have
No,
written.
005, 005.
Okay.
Influence factor is 0.005, right? Already given it is, and it is
Yes, yes, it is correct, sir.
okay. Okay. Next question. Now answer this question by yourself. You will tell me.
Sir, the foundation is flexible. Okay.
The soil is clay or sand.
Uh, Sir, I think it is clay because it deform more in center.
Listen, the deformation is not. This is not the deform. This is the settlement, right? Settlement is more at the center or at the edges.
Yeah, at the center. Yes.
Center. What are you saying? This is the settlement, right? Here, this
Yes.
was the settlement. This is the settlement, right? This part is the settlement. So it is more at the center or more at the edges. Hello?
Yes, at the edges maximum. Yes.
Here, what is the in which
Yeah.
part is the settlement more? Center
So
or
it
the
should be
edges?
same, sir.
Yes, sand. So settlement, this is the magnitude of settlement at center, and this is at the edge. So less magnitude of settlement at the center, that means more resistance from the soil at the center. That means the contact pressure distribution, if it was rigid, would have looked like this. More pressure at the center. So it is sand. Flexible footing on sandy soil. Okay. Now, Mohr-Coulomb theory, I think you know. Do you know Mohr-Coulomb theory? Shear stress chapter. The critical shear stress of failure. Please tell me if you know or not. Otherwise, I'll just.
Long back I study, but right now no, don't remember.
Okay, fine. So this is the equation. Anyway, this is the equation tau equal to C plus sigma tan phi. This is the shear strength. Shear stress at failure gives us the shear strength. So it is dependent upon the properties of material C and phi, and also dependent on the normal stress on the failure field sigma n. So both of the above is the correct answer. Okay, both of the above is the correct answer. Next question was okay. Just a moment. This is recording. Yes. Unconfined compression test is generally applicable for any answer you have for this. If you don't have, you can say. If you don't have any answer, I'll just start right away.
No, no, sir.
Okay, it is generally used for saturated clays. Okay, because this is the equation we get, sigma 1 equals to 2c tan 45 plus phi by 2. But when we do unconfined compression test, after multiple testing on the same identical specimen, we get the same value of sigma 1. So this equation becomes one equation and two unknowns. It is difficult to solve numerically. Okay, so we consider this phi equal to 0, and that is the case for saturated clays. So this is generally applicable for saturated clays. Okay, I believe we haven't solved this sum also, isn't it?
No, sir.
So this is the case of unconfined compression test where this is the plot. Okay, this is the plot, and this is the value of normal stress. This is the value of normal stress, which is the unconfined compressive strength, and this is the value of shear stress tau axis. This is the undrained cohesion, shear strength or undrained cohesion. Now in this case, the initial area A1 will be equals to how much? Pi by 4 d square, pi by 4 into 4 square 16. Okay, that will be 12.57 centimeter square. The value, the area at failure A2, that is equals to A1 divided by the strain 1 minus del L by L. There is a strain. So del L equals to how much? This is 1 centimeter del L, and this is the length of the sample. So you solve this, you get the area at failure approximately 14.21 centimeter square. Now why to find out this? Because we need to find out the unconfined compressive strength, that is equals to load by area. Load is 465 Newton. 465 divided by 14.21. Okay, 465 divided by 14.21. If I solve this, 465 divided by 14.21, yes, 32.72 Newton per centimeter square. Or if you convert this to MPa, it will be 327.2, sorry, kPa, it will be kilopascal. Okay, now you see the value of QU is the diameter of this Mohr circle, right? The value of this UCS, diameter of the circle, right? And the value of this CU, undrained cohesion, is the radius. So to find out, we have already found out the unconfined compressive strength, that is QU. Now what is the shear strength? It is the undrained cohesion. So CU is the radius, which is half of the diameter, which is equals to QU by 2. Okay, that will be equals to approximately 163.6 kilopascal. Okay, I hope it was clear. Anyway, if you don't remember, you can just note it down and just check it, correlate with later when you again do it. Okay, study the theory again. Okay, next question. You haven't solved this one also. Anyway, here the failure plane angle is 50, so alpha equals to 45 plus pi by 2 equals to 50. Solving this, we get phi equals to 5 to the 10 degree. So here we have already got the values of cohesion and friction, and value of friction. Now the cohesion is left. So we know from triaxial testing, sigma 1, that is the axial load, axial stress, sigma 3 confined pressure, tan square alpha plus 2c tan alpha. Okay, now in this case I have mentioned it is laterally unconfined, so it is sigma 3 equal to 0. So rearranging this equation, you get C equals to sigma 1 divided by 2 times tan alpha. Alpha is 50. Alpha is 50, right? So you get the value of cohesion approximately 67.12 kilopascal. Okay, and sigma 1 is equals to 160 kilopascal. This is sigma 1. This is sigma 1, 160 kilopascal. Clear? Have you solved the question from earth pressure theory? This question have you solved? No, right?
No, sir.
Okay. So this was the retaining wall of a height of 6 meter. This is the pressure distribution diagram. So here I have mentioned restraint from yielding. Okay. That means it is earth pressure at rest. This is 6 meter. This is the thrust P0. And this is the base of the triangle. This is the pressure, that is K0 times the vertical stress gamma into H. Now what is K0? Coefficient of earth pressure at rest. Formula is 1 minus sine phi. Phi is 26 degree. Put the value, you get 0.5616. Okay. What is the lateral thrust or force per meter length of the wall? P0 is equal to the area of the triangle, half into base into height, isn't it? Half into base into height. solve it, you get a value 192.0 0.07 kilonewton per meter, not square, per meter. Okay, is it clear? If you have any doubt, you can tell me.
No, sir. Please proceed.
Okay, so this was uh, the earth pressure at rest. The last question was finding out the active and passive pressure. So active pressure means when the retaining wall is moving away from the backfill. It is less than the passive pressure when the retaining wall moves towards the backfill. So I have to compute the active and the passive pressures. So first of all, find out the coefficient of active pressure and the coefficient of passive pressure. Coefficient of active pressure Ka is equals to 1 minus sine phi divided by 1 plus sine phi, that is equals to 1 by 3 because phi equal 30 degree. And Kp, coefficient of passive earth pressure, equals to 1 by Ka, so it is equals to 3. Now I have asked you to find out the intensities of pressure, not the force, intensities of pressure. So that means in the distribution diagram only the base of this triangle will be the answer. Okay, so this intensity of active pressure will be equals to Ka times the value of vertical stress. Okay, 1 by 3 into gamma 18 into the depth of 8. Okay, so it is, I believe it is 48. This is h, 8 meter, 48 kilonewton per meter square. Okay, because it is pressure. And what is the passive earth pressure? Passive earth pressure is Kp into gamma h. So it is, I believe, 432. Please solve it and check it. Okay, Kp is equals to 3, gamma equals to 18. Kp equals to 3, gamma equals to 18, and it is 8. Yes, 432. Okay, so any doubt regarding this, session? Dheeraj, Raghuvanshi, any doubt regarding the session?
No, sir. When I study, mostly it will be
Yes,
clear.
when you do study, please correlate all these, theories and numericals. Okay, so thank you for attending the class. We'll again meet with the next session on the coming Friday. Okay.